Hello, everyone, and welcome to Engineered to Ask, brought to you by the College of Engineering here at the University of Nevada, Reno. This is your host, Anthony Kuhl, and with me today is Russ Renzas, Cleanroom Director here at the College of Engineering. Thank you for joining us on the podcast today. How are you doing?
I'm doing great. Great to be here.
Well, that's great to hear. Now, today we're going to dive into the world of nanofabrication, and Director Renzas here is going to help us get a better understanding of what happens on the other side of the glass wall to the cleanroom. But before we get into our main topic for today, why don't you tell us a little bit about yourself and what brought you to the field of engineering in the first place?
I became interested in engineering because when I was a kid, the Nintendo, the original NES with Mario jumping, came out in kind of the early 80s. And so that was something that I knew people that had one of those, and I knew that that had to happen somehow, right? And Mario jumps, there's computer chips, there's transistors involved, there's a display, there's electrons are moving. Even the controllers themselves, which at that time were not wireless, they have cords, so there's extruded plastics involved. So I was really interested in knowing how my Nintendo worked. And naturally, I was the kind of kid that every time if I got something for Christmas, it was, I just wanted the thing that was the most complicated to build, and then I actually never played with it. I'm just someone that wants to build things. In those days, you would rent a VCR. I took it apart and got in a lot of trouble. So I have always been interested in taking things apart and taking them all the way to their essence. And in my career, I've taken that to what some people would say is a bit of an extreme degree, but I've had a lot of fun in my career, I'll tell you that.
That's really interesting that you brought up the classic NES system because I actually still own one of those. Not the remake that they released in, I think it was like in 2020 that they remade the console in like a smaller format, but like the original one. And I really liked getting into the background of how to alter the games or how to like dive into the code of them.
Well, there's a really interesting book on how to replicate the hardware in an FPGA.
Really?
Yeah, I'm the kind of person that owns books like this. I've also read an entire like 300-page book on the game engine behind Doom and Wolfenstein 3D.
Oh, I love that engine, yeah.
Although professionally, I've actually taken this less so on the software side and more all the way to, all right, if you write a piece of code, what's happening? And what's happening all the way down to nature itself. So you add two numbers, okay, so there's some instruction set that executes that. Maybe there's a register that's being queried. You're taking information from one piece of the computer or whatever it is to another place. So what does that have to do with electrons? How does that physically happen? Because at some point, everything has to go to a physical level. Mm-hmm. If it's wireless communication, at some point there's an electromagnetic wave involved, and we have to generate and propagate and receive that, right? Mm-hmm. The motion of electrons, the motion of matter, is what we're manipulating to do that. And in a sense, engineering to me is about it's a sense of communion with nature. All my hobbies outside of building things are whitewater kayaking and skiing and cross-country skiing and all of this stuff where I spend a lot of time kind of just thinking about how nature works and interacting with it, engaging with it. And to me, engineering is another way of engaging with the natural world around us. Maybe the way that I like to engage with it is by figuring out new chemistries for atomic layer etch processes to improve quantum device performance. That's my interest. But it's all ways of how do we commune with and control nature? How do we put matter where we want it to be? How do we pattern it? How do we use matter and the operational principles of nature itself to build interesting things? And some of those interesting things may be really important for people's livelihoods and for health and the environment. Some of them might be Mario jumping or a Tetris piece rotating. That's fine too. But ultimately, if you think about it from that perspective, just to see Mario jump, the amount of fundamental science and understanding of the natural world around us to make that happen, to me is very beautiful. Like I really like that. I like to to draw that line.
No, that's like an interesting take to have because I haven't heard that before, that like connection between engineering and nature and that it's just another way of us understanding the natural world. That's so great.
Yeah, as a whitewater kayaker, I'm going to go surf kayaking right after this with one of my kids. And I'm always looking at how water flows, right? Well, if you look at the way that we make equipment for the processing and manufacture of semiconductor, photonic, and quantum devices, right? Well, we have gases coming in, right? Well, those gases have to flow. They bounce off things. Gases bounce off surfaces and sidewalls, and they have sticking coefficients, and there's eddies in gas flow, right? Just as there are in whitewater, in a rapid. I don't know how common it is, come to think of it, but I've always viewed science and engineering through the exact same lens as I view the whole natural world.
Moving into our main topic for the day, nanofabrication, and I'm glad you brought up semiconductors because that kind of leads us into that discussion. I know we have our clean room on campus, and based on some of what we've spoken about in the past, I understand it's used to sort of prevent particles in the air from damaging like delicate research projects, but maybe you could walk us through some of the work that can be done in that space.
Yeah, so the clean room itself is just a clean room. That means not a lot of dust. Why is there not a lot of dust? Because we're working on things where it's like if you have a road and the boulder is bigger than the road, you don't have a road anymore. For us, if you think about an electrical interconnect or something like that, it's very similar. So if I have some wire and it's only a micron wide, it's going to be a problem if I have a piece of dust that's 10 microns wide that lands on that and may land on it between steps such that I'm not able to pattern that wire properly or even deposit the metal properly. The metal's going over a piece of dust. We clear roads first, right? We get everything clean, and then you put the road down. Similarly, we need to get rid of all the boulders and things and clear a path, and then you start putting the asphalt down. So it's the same kind of idea. I originally got involved in nanofabrication both through my undergraduate. So I did my undergrad at Princeton University in electrical engineering, which is the department I'm at here at the university, and then did my PhD in physical chemistry because I wanted to go even more fundamental. But throughout that, it's a question of, again, how do we manipulate matter to make interesting things happen, to make electronic devices function? So the way we go about that is fairly straightforward, actually. You have a piece of raw material, which is, it may be silicon, but it can also be other materials. And people outside the field often forget this. Yes, silicon is the substrate for CMOS, complementary metal oxide semiconductor circuits, right? That's the most common substrate. That's the 300 millimeter. That's TSMC. But there's actually a lot of other substrates that we can use in a nanofabrication facility like ours. We can use things like lithium niobate, aluminum oxide, sapphire. People will use quartz. They'll use all sorts of things. It just depends on the type of device you're trying to make, actually. Gallium arsenide, gallium nitride, sometimes one material grown on another. So whatever it is, the material that you're starting with, we don't do the material growth here. It ends up looking like a thin disc somewhere like 500 microns or something in thickness, plus or minus a factor of 2-ish. It's about that thick, and it can be anywhere from a small little piece that's maybe a square inch or a square centimeter. In our facility, we go up to 4-inch diameter, which is 100 millimeter. If you were doing like mass volume production, which we are not, we are a research institution, you would go up to 300 millimeter. But you take that wafer, so this disc, you clean it, generally speaking, in acids. The acid of choice depends on the material that you're trying to do. And then you need to go through a process of depositing material or modifying that material in some way. So how do we do that? The first step, we deposit material. So say I want to put just aluminum interconnects to get from electrons from one place to another. Great. So there's a few ways I can do that. One is I can boil off the aluminum onto the wafer. That's evaporation. There's a few ways of doing that. Thermal or using electron beams. Don't always need to use electron beams for aluminum, but if you're doing some high melting point material like platinum, you kind of do need to use an electron beam. So you have some emitter in an ultra high vacuum environment in a vacuum chamber. That emitter emits electrons, you steer them and concentrate them with magnetic fields. And then that concentrated electron beam is what's melting your material. You need to be in ultra high vacuum in that case because otherwise those electrons would collide with gas molecules and you wouldn't get the flux into the material. You could also do what's called sputtering, which is when you take a metal plate of that material, could be aluminum, niobium, whatever, tantalum. And in that case, you have back pressure of argon. You hit it with a plasma, which ionizes the argon. And then you use an a bias on the target to slam that argon into the aluminum plate or the niobium plate or whatever it is. And then that stuff starts flying off, just like you were sandblasting and you see the dirt flying back at you, right? So in this case, the material is flying back at your wafer and it lands there. the advantage of that technique is a little more control over quality and parameters of the material that's been deposited, things like stress. And also you can do oxides and nitrides and some other things. You have to change how you bias the material a little bit because of charging issues. But so anyways, you end up with some wafer that's now coated by, call it 100 nanometers of aluminum. So now I need to pattern that. So what am I going to do? Well, I can project an image onto a photosensitive material. So we take a material called photoresist. We spin that or deposit it. There's actually other ways of doing it, but in our lab and virtually every other lab, certainly in academia, it's spin coated. So it's just a little polymer goop. You spin coat it, you end up with something on the order of a micron thick. That material is photosensitive. We do this in a room that's, if you ever see the yellow light room, there's a room in the fab that looks kind of yellowish or amber colored.
Yeah, I've seen that.
Yeah, it's because the photoresists are all designed, in the early days of all this, everyone used mercury lamps for the photoresist exposure, and they have emission peaks at certain wavelengths that are all more energetic. So it's like we do 365 nanometer. So we just need to filter out that the lower wavelength, higher energy light, so that we aren't like, if I had my photoresist in this room right now, which is conventionally lit, all of the photoresist would be exposed, right? Mm-hmm. Because there is the light that photoresist is designed to be sensitive to in the light fixture above us. But if I'm doing 365 nanometers, then that yellow light, I'm filtering out all the blue, right, which is the more energetic light. And so therefore, I'm able to work with the photoresist without the risk of it being prematurely exposed. So then I take that. I use, in this world, there's a million, I won't get into all the metrology techniques, the way that we measure the thickness of the photoresist and the stress of the films and all that, but that's a whole world that actually I originally came from before I got into this stuff. I built the fab for a superconducting quantum computer company that went public, so I got very deep into that world then, but before that I really did characterization more. Anyways, so I've got this photosensitive material, and I selectively expose some regions. So I take some mask that's got a pattern already in chrome that's made through some other processes. Or in our case, we have a maskless aligner, so we'll just use a series of mirrors, DLP type style. And then I expose the areas I want to. Those areas, depending on the type of photoresist, are either cross-linked to make them stronger, or they're broken up to make them easier to remove. You put them in a developer. The developer selectively removes some of the material, and now you have a pattern of photoresist on top of this metal film. With the pattern of photoresist, great, well, that's blocking some areas. So what am I going to do? I'm going to go and etch that. Sometimes you can use a wet etchant. Actually, KOH, potassium hydroxide, works for silicon. It leaves crazy 45-degree angles, and the pictures are cool to look at. Mm-hmm. You could do a chemical etch, a wet chemical etch of aluminum, but a lot of materials you can't, and there's some reasons why you might want to do other things. So the most common thing, what's really done in industry, is we use what we call a dry etch. How do you etch something in that way? Well, aluminum, as an example, forms, it's a solid, and you want to react that solid with some kind of a gas, some reactive etchant material, to form something that is volatile. So this is where chemistry comes into play. And earlier I said I was a double E, but my PhD was actually physical chemistry. So I kind of live at the boundary of these worlds. Material science is a great field for people in this world, as is double E, but so is chemistry, actually. So I'm just doing a reaction. So earlier we were saying aluminum. Aluminum and chlorine, if you react those together, you'll get aluminum trichloride. Aluminum trichloride is a gas, or in ultra-high vacuum, maybe you might have to heat it up. I don't remember off the top of my head. But So that gas will etch the aluminum in the exposed areas. It will not etch the photoresist, or at least it will etch the photoresist slow enough that you only remove that you can stop and remove all the aluminum, the exposed aluminum first. For silicon, if you want to etch silicon, it's SF6. So silicon is, of course, a solid, but SiF4, silicon tetrafluoride, is a gas. Now, SF6 actually is not a particularly dangerous chemical. Chlorine's dangerous, but if I just flowed chlorine into the chamber, that actually wouldn't do anything to the aluminum. It's the power of the plasma. So now we get into electrical engineering again. So we can essentially use antennas, more or less, to excite a gas in a way that forms a plasma. A plasma is just a conductive gas. Essentially, you've stripped an electron that is now freely moving relative to the gas. So in the case of argon, if you have argon in a chamber and you dump a lot of energy at the right frequency into it, which is around 13 megahertz typically is the most common, you'll get argon plus with a sea of electrons. Well, what's nice about charged things is A, they're very reactive. Argon's not, but chlorine, Cl minus, ClO, if it's oxygen, you go from O2 isn't particularly reactive, but I assure you, if we had any free oxygen atoms out here, or oxygen radicals or ions, they would, in this room, they would have reacted instantaneously just about. So we create these more reactive species. SF6 is, we can breathe it. It's not reactive at all. You hit SF6 with a plasma, now you've got every fraction you can imagine, SF4 minus, F2, F minus, F, all sorts of crazy stuff. And now those free radicals are what are reacting with the material. And that's what's doing the chemistry. And so in that case, now, okay, we've come up with some process for this. Maybe we can use an electrical bias on the substrate and start smashing those. They're charged in many cases. So now you can promote physical energy. If you have argon in the mix, you can just use argon to blast off material as well as you go. So by kind of creating this mixture of physical and chemical energy, all enabled by the plasma's ionization of things, you can do all sorts of interesting etch processes. And that's actually the etching that's happening that forms the pattern on the wafer. Then you just need to strip the residual photoresist, which you can do in a chemical like DMSO, dimethyl sulfoxide, or you can do that in what we call an asher, which, again, pretty simple. A fireplace is an asher, right? If you burn wood, you have oxygen and some hydrocarbon fuel, and you put a lot of energy into it. Now you get ash. Well,
exactly, yeah.
Okay, well, why don't I just flow oxygen? If I have photoresist, which is a hydrocarbon of some kind, same as wood, I flow oxygen in, I put a lot of energy into it with plasma, heat, whatever. So now I have these reactive oxygen radicals. Well, they're going to form CH something plus O2 is going to give you water and CO2. And that's what comes out. We're literally we consider it ashing, but really it's just a very clean combustion and you're kind of removing all of that material. Then you now have a patterned layer on your wafer, and then you can go ahead and do the next thing. And that series of processes with some differences, like if you're doing photonics, you often will have a dielectric. You'll use there's chemical reaction ways of depositing SiO2 and silicon nitride and some other materials. There's atomic layer deposition methods where you're cycling different chemicals to generally deposit on the order of about a third of a monolayer, one atomic layer at a time to one layer. There's some steric hindrance reasons for that. But so you can conformally deposit single atomic layers. There's atomic layer etch processes, which is a research area of mine, to etch and remove single atomic layers. So you kind of get into these more complex versions, but they're sort of the same thing. You've cleaned a wafer, you deposit some material, you put a pattern on it, and you etch it. And then you kind of re-clean it to get back to that clean state and go do your next thing. And so by going through that process over and over and over, we create all of the devices of today. Now, there's other steps in planting ions and all sorts of stuff, but the fundamentals are the same. And you can basically learn those fundamentals in our lab, and some version of those processes is the same thing as the processes that are happening at TSMC or the quantum computer company that I built the fab for, or any of those other places. It's the same fundamental ideas.
That's so interesting. So that's like the full process, at least for setting up the basics of like the wafer itself for a superconductor.
Well, yeah, I mean, actually, so aluminum, the example I used was aluminum. Aluminum, we don't think of, everyone will read in the news, there's some high temperature superconductor. Well, if your device operates at a low temperature, you don't really care about a high temperature superconductor. So like when I was doing superconducting quantum computing, there's reasons to do with the energy splitting in a qubit where you need to be down at 10 millikelvin anyways, so 0.01 Kelvin. Mm-hmm. Aluminum superconducts below 1.1 Kelvin. So aluminum's a superconductor.
Oh, yeah.
From
so
my perspective.
Yeah.
Niobium, I think the TC, the superconducting critical temperature is like 9 Kelvin. Depends on, it can vary a little bit depending on the deposition parameters, but 9 Kelvin's way above what you need. There's a lot of devices that operate at 4 Kelvin. Well, niobium superconducting, fine. Maybe you can't use aluminum in that application, but niobium you can use. I think it's the beta phase of tantalum. Might be the alpha. Crystallinity matters a lot for superconductivity. Yeah, there's a ton of stuff that's superconducting at different temperatures. Yeah.
Wow. I think you've really given us a lot to chew on, especially for our listeners, as far as the world of nanofabrication and like setting up a semiconductor, which I think is great. That sort of information is awesome to have out there. Going forward from there, what sort of topics would you recommend that if they're looking to get into this field in particular, what sort of things should they be exploring?
So there's a huge number of disciplines that go into this that are, I think, nearly anyone in the field of engineering in any capacity probably is developing a skill that is useful in this world, maybe in different ways and in different parts of this world. So if you were doing kind of computer science, well, think about all of the programming that has to happen to control these tools, right?
Oh, yeah.
And also, people will learn like Python, all these very higher level programming languages, right?
Of course.
Well, all right, but how does that get translated down to the machine level? How does that actually interact with the hardware? So as you drill down into the real assembly language stuff, how do we compile, how do we interact with the hardware? So you can go that direction if you were a computer scientist. Or maybe you're interested in optimization and control. Well, there's a lot of optimization that has to happen of the circuit designs. Maybe you're interested in modeling, in modeling the electrical circuits and electrical systems, or computational fluid dynamic modeling, right? Plasma dynamics modeling. So you might be interested, if you were a theorist, maybe you're interested in all these packages that model the behavior of the quantum devices themselves, because quite frankly, I'm living in between electrical engineering and chemistry. I don't know that much about the actual design. I never really did a ton of mass design. I've done a little bit for test structures and things. But there's people that are really experts in that. Maybe you're really interested. You're like, look, I love all this machining. I love to design things in CAD models and all that. And I want to do these electromechanical systems. Cool. If you go look at the tools, they're really complicated. There's a lot of parts. And those parts, how they ground to different surfaces, the coatings that are on them, how those interact with all of the chemistry that's happening inside, that matters a lot. So maybe you get into the vacuum systems, the design of the tools themselves, right? Maybe you're doing the electrical work, all the PLC work that's controlling how these tools interact. And there's a lot that goes into operating a tool properly. Maybe you're like me, you're really interested in the chemistry and understanding how the chemistry interacts with the performance of a device. So then maybe you're in materials science. So you're learning a lot about crystallinity and about the characterization techniques. We use an enormous suite of characterization techniques to learn about material at the atomic scale. XPS to look at the oxidation state of things. Scanning electron microscopy, of course. XRD, X-ray diffraction, to look at the crystallinity of things. Atomic force microscopy to look at surface roughness and some other properties. So there's just an enormous amount of stuff. But like concrete would be a little less relevant, right?
Of course, yeah.
But at some level, I think you want to look at it as the tool and what's happening inside the tool, and then why we design something the way that we design. And really, everyone gets better at all of these things by understanding the other pieces. A lot of my work in developing these new methods is based around an understanding of what affects the device performance. Well, in that case, I have to work with people who do the design and the device level test to understand what actually matters. What problems can I work on that will make something a little bit further up that stack of abstraction more effective? Ultimately, our understanding of nature and matter is what limits device performance. So I just kind of view it that way as well. Like the more we fundamentally understand, it's interesting. I've had an interesting career in the sense that it's pretty cool to like discover something that gets used for many, many, many years. And although in engineering, in science, we kind of put them as more distinct, they're really not. If you're engineering at the edge, not just replicating what someone else made or tweaking what someone else made, but really engineering at the edge, trying to understand how can we create things that couldn't be created yesterday And if you're on kind of the applied piece of science where you're thinking, all right, well, maybe I'm not looking at outer space. I was really nearsighted, so I couldn't see the stars. So I think I never really looked at outer space. If you can't see it, it's hard to be interested in it.
I mean, same here, so.
Yeah, well, I'm nearsighted and I work on, nanomaterials, so, you use an electron. Maybe that's just me. I really think that being nearsighted played into it all. But it's pretty cool. Like, I've developed processes that I know are being used to make quantum devices today, like almost certainly today, definitely for the last many number of years. And to know that your work is both fundamental, but also is allowing people to make new devices. We developed a way of etching silicon carbide at the atomic scale that really has the potential to improve a lot of power electronics and certain kinds of quantum devices. And it's pretty cool. In a lot of fields, whatever it is that you achieve is kind of limited to that time and that place. In our world, I think, especially someone that's now, I'm in my mid-40s, I can look back at things that I did 10, 15 years ago, and the impact of those things is continuing to grow. Even though when I first did it, maybe it didn't have a huge impact at the time because this stuff is all kind of longer time horizons. Mm-hmm. But then I have these things that are sort of following my whole life. I'm getting citations on papers that I submitted in the late 2000s.
Wow.
They're 20-year-old papers, and people are still reading those and using those. And so there's something about
having that walking legacy that kind of follows you.
Yeah, I have kids. My kids, when they're in their 60s or whatever, much later in life, they can go back and read stuff that I did that's in the public domain and see my personal contributions to human knowledge and human progress. And they can also go and look at all of the people that followed along. They can look at the citations of those and the citations of those. Mm-hmm. And I think that with life being, you never know what's going to happen in life. And it's nice to be able to have things that you can point to. You can say, hey, look, it's still there. It's in a sense, I don't know if knowledge is always permanent. Mm-hmm. If the planet explodes or something, there's probably limits to that. But it's nice to have a sense of permanence about the work that you do. And I have liked that about science and engineering, the sense of permanence.
Wow. That's an amazing place for our discussion to have gone to. I do often think about the role that legacy often plays into engineering and the work that is done in our college, or just in the field in general. Just the idea that almost everything that's done when it comes to inventing new concepts or new machinery, that it's always being iterated upon, even if it's not by the same person, but just having those concepts continue to live on and grow is so fascinating to me.
Yeah, it's really fascinating. I mean, for me, the quantum computer company thing was a really interesting experience because when I started there, it was an empty warehouse, and I was just told to go build a fab, and we were going to make qubits. This was in 2016, mid-2016, and it took us about a year, but then we started making devices on it. Well, it's been, 9 years since then now? And there's still, that company still operates. Rigetti Computing, you could go buy shares today if you want. And the fab, it's expanded. They've improved it for sure. They have some incredibly talented people there now. More or less, I don't know, they're probably pretty similar to who we were, but the people that are carrying that forward. It's really cool to me to know that the work that I did in those early days, the inventing new processes and things, it's being improved and iterated upon. I go to conferences and I'll meet people from the company that I didn't interact with at all. I didn't even overlap with them. I was gone before they started. And they work in a place that I helped create using processes that evolved from processes that I helped invent. I think that's really cool. There's a sense of permanence and of legacy for sure.
Thank you so much for coming on the podcast today, Russ. And a big thank you to everyone who's listening out there. We greatly appreciate you stopping by. If you'd like to know about how you can get involved in this sort of research and more here at the University of Nevada, Reno, you can visit our website. The links will be in the description. And if you liked this discussion and would like to hear about other interesting engineering topics, please like, comment, and subscribe. It's the easiest way of keeping up with the series and letting us know that we're doing a good job. This has been Engineered to Ask.